All right. Thank you, Katja, for the introduction, and very much thank you both Katja and Knut for giving me this opportunity to present my work. So indeed, I will be talking about the geometry of gas giants and inverse problems in both of these things combined, and my talk will be based on basically two articles which I've written in collaboration. The first one in collaboration with Martin de Hoop, Jonas Ilmavirta, Reid Macheo. This is about gas giants. And then I will touch upon some other work that kind of goes beyond gas giants. It's called Lipschitz stability of travel time data, which I wrote in collaboration with Jonas Ilmavirta, Matti Lassas, Teemu Saksala, and Andrew Sedlock. So let's get started. Oh, hold on. Now it works. Good. Okay, so my talk will contain like roughly 5 parts. We will start with the most important one and discuss what this gas giant geometry is, and particularly like where does it come from. So if you catch nothing else from my talk, this is the most important part. Then we will get ourselves a little bit more familiar with how this gas giant business works. So we will look at some basic properties and get a better intuition into what these things are. So, and then we will dive into a little bit of deeper topics, let's say. So we will take a closer look at boundaries of gas giants. We will look at a couple of inverse problems, the X-ray transform, and also these travel time inverse problems. All right, but we start from the beginning. So gas giant geometry. Okay, so from our perspective, we want to model like wave propagation on gas giant planets rather than rocky planets. And what is the kind of like the basic first thing that you realize is the difference between the two? So on a gas giant, your density of the matter goes to 0 at the boundary of the planet or at the surface of the planet, whereas it doesn't on a rocky planet. So in the case of a gas giant, we will see that somehow the sound speed has a square root type of behavior in the distance to the boundary. And I mean, I will explain later where this comes from, whereas on a rocky planet, it's kind of like a linear type of thing. Okay. So our main questions I want to answer and address today are basically that how do we incorporate this kind of a vanishing of density or the sound speed profile into a kind of a geometric model for wave propagation on gas giants. And then we want to explore how different is this kind of gas giant geometry from a rocky planet geometry in this sense. And then, of course, can we solve some inverse problems in gas giant geometry? Right. So let's get into it. The starting point, we will say that our planet is a smooth manifold, and we will model a sound speed by a Riemannian method. Okay. The geometry that arises is this type of geometry where the distance is measured in travel time of seismic waves. So these are basically the same principles as how you would model like wave phenomena geometrically in rocky planets, but the difference is now in how this sound speed really behaves. So let's dive a little bit into physics as well. So for example, we can take our manifold or our planet to be this close to unit ball in, let's say, Rn, and then we can consider a Riemannian metric, which is given basically by the sound speed to the power -2 times the identity matrix or the Euclidean metric on this ball. So now this is a kind of a radially conformally Euclidean type of model. So typically, what physicists do in these kinds of business is that they model these planets as something known as polytropes. And what does that entail is that there is this kind of a power law type of relation between the pressure and the density of the planet. This is called the polytropic equation of state. There is some context index different for different planets usually. It's called the polytropic index, which is the model parameter, if we put it that way. And then this polytropic equation of state comes usually kind of coupled with certain conditions which talk about this kind of an auxiliary function x, which is related to the pressure and the density. via also power type laws, and also it satisfies this the so-called Lane-Emden equation, which is a well, in this case it's a ODE. Doesn't really matter what the ODE kind of models exactly, but what is important about this solution, so this auxiliary function x, is that it will be positive in the interior of the planet. It will be zero exactly at the surface or the boundary of the planet, and its derivative there is non-vanishing. So it goes somehow cleanly through the boundary, so to say. Okay, so that is kind of the physical model behind this business, but how do we get this into mathematics? So let's try to do that next. So the important thing about all of the information in the previous slide is that now from this information we can compute the sound speed basically in terms of the pressure and the density. So it turns out that the sound speed of such a planet is given by the so-called, I think this is called isentropic derivative, which is kind of like a root of the derivative of pressure in rho. And you can combine the information from previous slide to express it in a couple of different ways. So in particular, you see that there is some constant k now having 3 primes times x to power 1/2. And this x was a very particular type of function. Okay, well first, now our model was that our Riemannian metric is conformally, radially conformally Euclidean. So we can do a little bit of a computation and divide and multiply by this x function. And we will find that since this x has a square root type behavior related to c, then if we denote this guy by g bar, then this will be something that has nice properties as it goes to the boundary, whereas this first this conformal factor in front, x to power -1, that will blow up at the boundary. So the particular kind of square root to sound speed type of behavior is important here. So what did we observe? We observed that gas giant geometry is somehow conformally singular at the boundary of this planet with a particular power. And indeed, what I mentioned on the first slide, that this sound speed is comparable to basically the square root of the distance to the boundary. So as I mentioned, the properties of x on the previous slide, that basically means that it's some kind of a distance function to the boundary. All right. So now we are ready to build a mathematical model out of this. So we generalize our situation a little bit. So no more spherical symmetry assumptions, but let's just start with a compact and let's say simply connected smooth manifold with a smooth boundary. And then we say that a Riemannian metric on the interior of this manifold is called a gas giant metric if it can be expressed in this form. So G will be equal to G bar divided by x to power alpha, where now x is a smooth boundary defining function, positive in the interior, 0 at the boundary, derivative doesn't vanish at the boundary. Also, this G bar has to be a kind of like a smooth background metric, which is smooth up to the boundary. And now we allow this alpha not to be just only minus or 1, as it was on the previous slide, but we can allow a little bit of a wider range. So alpha can vary between 0 and 2. And so that is gas giant geometry basically. And then there's also this kind of a let's say a newer development where you can allow alpha here to be actually a function also on the manifold. And in a sense, this would then correspond to somehow a rotating planet model, because well, in physics, usually that in those situations you end up in places where you need to allow your holotropic equation of state to vary within the planet. So then you would get different alphas for different regions of the planet. But we'll return to this a little bit. Our main focus is going to be on the case where alpha is a constant. All right. Is there any questions on this model yet, or should I go to the basic problem? All right, let's continue. So basic properties. This is a condensed presentation of what's happening. So on our terrestrial planet, our rocky planet, the sound speed profile is always so that it's bounded up from below and bounded from above at all points of the planet. On a gas giant, we have this kind of like a fractional, almost alpha close to 1 type of blow up at the boundary. And then if you go alpha, you would put alpha equal to 2, you would end up something called asymptotically hyperbolic geometry, basically. So in some sense, gas giant manifolds lie somehow between standard Euclidean, standard Riemannian manifolds and somehow these asymptotically hyperbolic manifolds. And terrestrial planets have finite volume. This kind of gas giant model can have finite or infinite Riemannian volume, whereas hyperbolic geometry always has infinite volume. But there is also certain features of gas giant geometry which say that it's not a direct kind of like an interpolation between the endpoints alpha equal to 0 here and alpha equal to 2 here. So clearly, smooth Riemannian geometry has bounded curvature. And on asymptotic hyperbolic manifolds, you always have your curvatures approaching -1 at the boundary, or sectional curvature, I should say, to be more precise. But on a gas giant, your curvature always blows up at the boundary. And what is fun about this is that somehow because this blow up is so mild or mild enough, our travel times of waves can be finite. Whereas if you want to actually reach like the boundary of an asymptotic hyperbolic manifold, you need to travel for infinitely long. So this is in a nutshell the picture that we're looking at here. All right, so let's try to explain a little bit of what these are. Okay, so some features of gas giants. First one, there is a orthonormal basis of sections of this tangent bundle. So that the sectional curvatures of two planes spanned by pairs of these vectors are always asymptotic to either one of these numbers. So this is a computation you can do in coordinates, and what this precisely means is that your sectional curvatures will blow up at the boundary, and in particular it means that there is no kind of, for example, constant curvature gas giant model out there. What is also important here is that these blow-ups happen with specific powers of alpha. Or like specific coefficients which depend on alpha, so that will be kind of important later. The Riemannian volume of such a manifold is always is finite if and only if this alpha is less than 2 over the dimension of our manifold. So that's a basic fact, which you can also compute just by doing a coordinate computation. And one nice thing about gas giants is that somehow if you cut your manifold at an epsilon amount inside, then you create a surface or like a hypersurface inside a submanifold, which is always strictly convex from the inside. And this usually has nice effects on when you try to do geometric inverse problems. So this helps you with kind of like regularity theory. Let's put it this way. Okay. More, there is kind of two competing types of coordinate systems near the boundary. So most of our analysis is going to be done near the boundary of such manifolds. So then we want to use some kind of nice coordinates there. Usually people use boundary normal coordinates. That is not exactly available for gas giants, but we have something that is close to it. So basically, there is one set of coordinates, let's call them x and y, so that you can kind of write your g bar metric in boundary normal coordinates, and then you get the g by dividing by this x to power alpha factor. Okay, so that's nice. These types of coordinates are also available on a asymptotic hyperbolic manifold, but the next type are not. So if we do a small change of coordinates here, so let's let x be s be x to power 1 minus alpha over 2, which is, this is a little bit singular at the boundary, but if we can allow this if we are just like ready to change our smooth structure of the manifold a little bit. So this is all fine. So in this case, you will end up in this form, which is basically boundary normal coordinates. Other than that, this second factor here is a little bit singular. So you have s to power minus beta, where beta can be computed from alpha in this way. And this is clearly not available, for example, on those asymptotic hyperbolic manifolds, since if you put 2 here, then this coordinate change is not a very good one. All right, so there's basically 2 ways of looking at boundary geometry on a gas giant. Then we consider a little bit of, let's look at a little bit about these geodesics on gas giants. So we can consider the geodesic Hamiltonian, which now in these sets of coordinates can be written either in this way or in this way. And I will talk about trajectories of the corresponding Hamiltonian flow on the next slide. So we will divide them into components according to these coordinates, where now psi corresponds to x and eta is a coordinate that or a covector that corresponds to. Good. Okay. So what do geodesics on a manifold like this look like? Okay. So let's say we start our flow at sufficiently close to the boundary. So at distance, let's say x, which is less than epsilon to the boundary. And also we start in a direction which is kind of pointing towards the boundary. Then what you can prove is that the trajectory or the geodesic will converge to a unique point on the boundary, and it does so in a finite time, always in a finite time. So you basically, this means that your boundary is actually like reachable in finite time with the flow. This is also a fact that is not true on an asymptotic hyperbolic manifold. Of course, it's true on a, let's say, compact smooth Riemannian manifold with boundary. And you can also prove that this eta vector, eta part of the coflow has some nice limit at the boundary. Okay. The exit time function. So this exit time here depends smoothly on all of these initial conditions you set on your trajectories, and it has a leading order asymptotic as you bring down the starting point of your flow. So, well, in all details, this is you can prove that this is a polyhomogeneous function with some particular index sets. Okay, so this is nice to know. At least when you bring your x, the starting kind of height down, your travel times will go to 0. And also you can define this is what I call the endpoint mapping here, which takes some initial values and maps them to these endpoints along the flow. And this will give you a nice diffeomorphism from this surface to the boundary and back. So in total, all of these 3 conditions, I would say that tell you that our geodesic flow on this manifold is very well defined. And it has some certain nice properties. So to bring this to kind of more pictorial form, here on the right-hand side, I have drawn a couple of like geodesics. Let's say we have flattened out the boundary, and now we start at epsilon height here, and we consider geodesics for different values of alphas, and we shoot them kind of vertically outwards. So then they will all look like this. So from here, you can't quite see it, you can almost see it, but they all come normally to the boundary, for example. And if we now look at these coordinates s and y from the previous slide, you can see that your co-spheres in the cotangent tangent spaces will become kind of flatter and flatter ellipses as you approach the boundary, and then as you hit the boundary, something singular happens, and your co-spheres kind of blow up into two planes essentially. But nonetheless, you can get like a diffeomorphism condition from here to one of these and back. So the flow is still kind of well defined essentially. Right. So that should give you some kind of a picture of what gas giant geometry, gas giant basic properties are. What does the geodesics on a gas giant look like? Good. So next up, let's consider the boundary of a gas giant a little bit more. So as we have now established, basically, is that this boundary of a gas giant always lies at the finite distance from the interior. You can flow there in finite time. But as is business with this kind of conformally blown up metrics, is that the blow up of G somehow always affects how this boundary sits inside the manifold, and more than that is that particularly affects the size of this boundary. So what I want to aim at is can we compute the Hausdorff dimension of a boundary of a gas giant? So what we want to do here is we can, for example, so if we take just a standard smooth Riemannian metric, then its Hausdorff dimension will always equal to its, or the boundary, Hausdorff dimension of the boundary will always equal the topological dimension of the boundary, which will be n-1, let's say. And in the asymptotically hyperbolic case, this is kind of a weird question, because it's not even clear like what the metric on the boundary should be, because it takes infinite time to reach the boundary. So let's say that it's infinitely far, the boundary, and also infinitely large. But now in this gas giant case, we should lie somewhere in between. So we can expect that something cool happens. The following computations are done in these coordinates. All right. So what we have here importantly is that there is this well-defined metric H0 on the boundary. So then we can use two different notions of distance between boundary points on a gas giant. We can use this H0 metric, or we can use the metric Riemannian distance function corresponding to the G. So basically, you can measure distances along the boundary with H0 or through the interior with G. And what you can prove is that there is a kind of like a power type behavior between these two distances. So there are some uniform constants, so that these two metrics are uniformly kind of or are Lipschitz comparable to each other with uniform constants when you put this power in there. And well, proving this is not very difficult. So what you do is that you look at your geodesics on this manifold, and you can approximate these by, let's say, quasi-geodesics, which go like with straight lines, this kind of like a broken line type of thing. So and then you optimize your epsilon here, and you find this power type behavior. Okay, and it turns out that this is basically all we need to compute our Hausdorff dimension. So here's the result. N will denote the dimension of the manifold. Then the Hausdorff dimension of an alpha gas giant is going to be the maximum of the Hausdorff dimensions of the interior and the Hausdorff dimension of the boundary. So the interior here is not extremely interesting, because it's just a standard Riemannian manifold. So its dimension will always be this n, but the boundary will have something that is some dimension that is possibly like fractional. So it has some kind of weird behavior. And now this is kind of a simple computation using the previous lemma. So our previous lemma states that these two metric spaces will be Lipschitz equivalent. Thus, they have the same Hausdorff dimension. And then there's this so-called snowflaking type of thing, that the Hausdorff dimension of a metric raised to some power, you can just flip the power to in front and put a -1 power there, and get the Hausdorff dimension of the not raised to a power metric. And then this will be equal to n-1 since H0 is a standard Riemannian metric on the boundary. Okay, so that proves this. What I think is nice about this is, for example, that now we know that since it takes only kind of the boundary distance function data to compute this Hausdorff dimension of the boundary, then we can always read off the alpha index from these boundary distances. So using these functions, you can always compute this one, and then from here it's a simple algebra to figure out what your alpha is. So now a good question is that if we have a variable index in our gas giant model, could we still do the same computation? So let's say we know this boundary distance function. Distance is restricted between boundary points. Can we now figure out what this variable index is at the boundary? So we will do that next. So now we consider a variable case where this is a smooth function, and we take some reference metric h. And what you can show is the following type of result, that for any boundary point, basically, if you're close to that point, sufficiently close, so construct some nice neighborhoods, then in these nice neighborhoods, you have locally these sorts of estimates, where alpha plus minus correspond to the maximum and minimum values of alpha in here. Okay, and then these constants here in these estimates are also uniform. So basically, you can get a similar result from before, but now you get it locally. This power type comparison to some metric on the boundary. So well, you prove this by basically locally comparing G to constant index metrics, and you can also arrange this in such a way that these maximum and minimum values go to this value of alpha at y if you shrink your neighborhood to vy. And now, since we have local estimates, we can compute the local Hausdorff dimension complement. And yes, we can. And okay, so what do I mean by local Hausdorff dimension? So this is something that measures kind of the Hausdorff dimension very close to a point y. So what you do is that you look at balls around this point, you intersect them with y, and compute the Hausdorff dimension of this restricted set with respect to the kind of subspace topology, basically, and then you let your ball shrink to a point. So this will define you a nice concept of a kind of Hausdorff dimension of a point. So then the corresponding result in this variable index gas giant case will be that your local Hausdorff dimension is going to be the same number as before, but now we look at alphas, but the value of alpha at y. And also you can prove as a kind of a corollary of this that the maximum, if alpha max is the global maximum of alpha on the boundary, then this Hausdorff dimension of the entire metric space here will be the same number, but you replace the alpha part with the maximum value of alpha. And again, it's very nice that now, if we have two Riemannian metrics, two gas giant metrics with variable index alphas, whose distance functions agree on the boundary, then you can compute for both of those metrics this Hausdorff dimension, for example, and then it's a simple algebraic argument to figure out that your gas giant indexes are the same. So I would say that this is kind of like our warm-up inverse problem, so to say. So you can figure out the gas giant index from boundary distance function data. Good. Next up, now we get into inverse problems. The first one is my favorite one. It's the X-ray transform. And so let's look at what this does. So now we are back to the constant index case. Alpha is equal to real number, and we will keep it that way from now on. Okay. So what do I mean by an X-ray transform here is that this kind of a function that well, it takes in a function and then produces another function on the space of geodesics of the manifold. So what you do is that you define if of gamma by integrating f along this geodesic, which goes now between any two boundary points. So these are maximally extended geodesics. They go between any two boundary points. And our theorem about the X-ray transform on gas giants is that if you assume your gas giant to be simple and your function to be smooth up to the boundary, then whenever a function f integrates to 0 over all maximally extended geodesics on a gas giant, then it has to be the 0 function. There is no other. So in other words, this transform is inject. Okay. I have highlighted here that we are assuming our manifold to be simple, but what do I mean by it is basically that there is no conjugate points in the manifold. It's non-trapping, so all geodesics always exit in finite time, even though we know that it's somehow true always if you start close enough to boundary and end up in the direction of the boundary, then you will exit in finite time. But now, of course, we want to assume that this happens globally, so that our like X-ray transform is even like well defined for this set of functions. And then usually you would add here something that guarantees that your manifold has convex bound. But we don't need to worry about convexity, because as I pointed out on one of the earlier slides, that this is in some sense automatic, because if you bring your boundary a little bit inside, you will always get convex sets. And in fact, if you let epsilon go to 0 in those truncated sets, then your second fundamental form gets larger and larger. So you get better and better convexity the more closer to you are at the bound. So we don't need to assume anything of this. Here I want to mention some related work. So for example, in asymptotically hyperbolic geometry, it has been studied this X-ray transform for functions, but not just that, also X-ray transforms of tensor fields of many order and rigidity questions and so on. And for example, I want to mention this work by Graham, Kiermaier, Stefanov, and Ullman. It's very much related to our work here. Okay. So a little bit about the proof of this thing. We use this so-called best of identities. I think maybe many of you are familiar with this, but let me still kind of explain the basic idea of what you want to do. So here your data is basically integrals of your function over maximally extended geodesics. So then what you can do is that you can define a new function u that is kind of the integrals of your function over geodesics, not just maximal geodesics, but geodesics starting at any point to the boundary. And that has the nice property that then if you differentiate it or hit it with the Hamiltonian vector field x, then you get your f back. So now this best of identity comes into play here, because you want to now study this so-called transport equation. It will be an equation on the co-unit sphere bundle of your manifold. You want to use this kind of a best of identity to argue that, okay, the only solution to such a problem with 0 Dirichlet values, so x hitting on u is minus f with u equal to 0 on the boundary, because f integrates to 0 over maximally extended geodesics. You want to argue that the only solution to that is 0 function, because then you would get that f is 0. So what you use usually for that is this kind of a best of identity. So this is L2 identity. There's some kind of derivatives of f, and also the curvature here is also right. So this is a L2 identity. So specifically, it involves the kind of Riemannian measures in this business, and also it involves this curvature term. And we saw earlier that curvature blows up on a gas giant, and also the measure blows up positively. So you can have infinite volume. So these are things that you need to deal with. So the kind of thing that we can do is we restrict to this set. Let's call it m epsilon, which is defined as the set where x is greater than equal to epsilon. And now since for very small epsilon, this boundary is even convex, so this now is a very nice manifold where you can do stuff. So for example, a best of identity on this manifold holds. So you have something called best of epsilon, and then you end up studying the limit of this identity as epsilon goes to 0. And you want to argue that somehow this limit makes sense. So basically it's ill-defined, because you will have some kind of smoothness and integral fluidity issues. Well, things get technical, but basically what you want to prove is that this u function, the integrals of f over geodesic, they vanish in some sense to a high order at the boundary of the manifold. I guess we should have boundary of the unit sphere bundle here, not boundary of the manifold. But nonetheless, you get the idea. So this is what you need to deal with in the background. A big thing helping in this business is the so-called boundary determination. Maybe you can prove that if your X-ray transform vanishes, then your functions at least have to vanish at higher order at the bottom. Okay. So this kind of approach is also used by Graham et al. In their approach, but our details of this analysis is quite different because there is certain properties on gas giants which are not just kind of interpolations between the asymptotic hyperbolic manifolds and the standard Riemannian cases. But nonetheless, I won't go into more details this time. All right. So that's the X-ray transform. So then I want to talk a little bit about the travel time or a travel time inverse problem. All right. So which kind of a travel time problem I'm looking at here? So this time I will be talking about this so-called travel time mapping. I denote it by RG. It's a mapping from the manifold into the space of continuous functions on the boundary. So it takes a point in the manifold and it produces a function dgx restricted on the boundary. So basically, your data consists of a collection of distance functions from interior points to all boundary points. So the travel time data is the image or the range of this R travel time mapping RG. And that is what we want to use as our data. And then the question arises: is a gas giant metric uniquely determined by the knowledge of this travel time data? And our result is yes. We do assume simplicity. In this article, I will touch a little bit upon this later, but the result is yes. So if you have any two gas giant metrics GI or G1 and G2 with possibly different indexes, so that their travel time data agree, then the indexes have to be the same, and also the metrics have to be diffeomorphic to each other isometric to each other via a diffeomorphism that is identity on the boundary. So, for example, in standard Riemannian geometry, these kind of results are very well studied. So Katsalov, Kurulev, Lassas in 2001 proved that such results hold for basically all compact smooth manifolds with boundary. And also this has been even studied by Helin, Oksanen, Lassas, and Saksala, that such results on closed manifolds as well. So this is very well known, but I think it's very nice that we can also get these alpha indexes here on top of other stuff as well. Okay, the steps of the proof. We are not going through the full hoops of doing such injectivity proofs as was done in the earliest results, but there is something simpler that appeared in this article. Ilmavirta, Liu, and Saksala, they use the so-called Meyer-Steenrod theorem. So let me try to explain how that kind of works. So the steps of the proof are that you want to prove that these RGI mappings are both isometries onto their image, for example, here. So you want to show that this mapping is an isometry and this mapping is an isometry. Okay. So what would that then give you is that since the data here on the continuous function side are the same, then you can define this function and it will be well defined. So you can go around here first by RG1, and then since the data are the same, you can go here, and then you can traverse back by RG2. And now, since this is a composition of isometries, it will be an isometry as well. So it's a metric isometry, essentially, and then you can promote it to a smooth Riemannian isometry just by using this Myers-Steenbrook theorem. That just straight away tells you that all isometries of this type have to be smooth, and they're Riemannian isometries. So those are the steps that you want to establish. So crucially, that these RGI mappings are isometric. And how do you do that? In the case of simple manifolds, this is quite simple. So first of all, you can show a Lipschitz estimate of this type for the RG mapping just by triangle inequality. So here we have the supremum norm of the difference of these travel time mappings, and if you write that out, you see directly by the inverse triangle inequality that it has to be less than this. Okay. And then by simplicity, you also get this kind of nice condition. So that if you have any 2 points here on your manifold, then there is a unique geodesic that connects these 2 points. And also you can extend it in a unique way to, let's say, some boundary point Z here. So then you will know that this, in this case, the point X has to be kind of in between of Z and X. So you will get this condition to hold. So in particular, for these sets of points, the other inequality holds. So together these two estimates then prove that your mapping is a bijective isometry indeed onto each image. Good. And then you can do the steps on the previous slide. And now I haven't told you how to determine the alphas yet, but this alpha is now we go back to the earlier slides again. So this alpha is determined because you can compute those rates of sectional curvature blow up by using only interior information. So after this step, you know that your manifolds are isometric. So you can determine the alphas. They have to have the same sectional curvature blow up rates and those constants there depended on alpha by an explicit way. So you can definitely compute your alphas. So that's nice. Excellent. But now I want to go a little bit further and also consider, well, let's say, basically the stability of this result, and also that can we go a little bit beyond simplicity. So now comes the step where we go a little bit beyond gas joint geometry as well. So as we saw on the earlier slide, that the key steps or the key features you need in this proof are that this RG mapping is an isometry, and this is very much related to somehow this like distance minimizing extensions of geodesics or some curves. And also we show that somehow metric geometry is very much enough, because you can, in your manifold cases, you can use those Myers-Steenbrook theorems to extend metric geometry results to smooth results. Okay, so let's just consider a metric space setting for a little while now. So we let XD to be a compact metric space, and we choose some measurement set. You can think of the boundary if there's a boundary on a metric space. So if this was a manifold, then you could choose a boundary here. But we choose some closed measurement set inside the space, and then we define this travel time mapping again, basically in the same way. Okay, and now we want to make sure that our like travel time mappings are isometries, but our result will not have to assume all of that, because we basically want to go beyond simplicity. So we want to have conditions of the following type. We want to assume that our metric spaces are going to be something that is known as pli or bli. So in the first pli case, we will say that we will assume that this travel time mapping is a local epsilon isometry, and bli case would then mean that the inverse of this mapping will be a local epsilon local isometry. And what do I mean by that is that, well, it's basically an isometry if you restrict to points which are a priori are close to each other. And I want to point out that, okay, my point is here is that we want to still talk about gas joints, so gas joints are included in this metric space setting, for example. But of course, there are many other examples. Okay. So then what are these flea and blee conditions really? So now with ilmavirta Lasse Sakla and Sedlock, last year we showed that such a flea epsilon condition, local isometric condition on the travel time mapping, is equivalent to the condition that if you have 2 points which are a priori epsilon close to each other, then there has to be an epsilon, there has to be a distance minimizing curve connecting those 2 points, which extends to the boundary in a distance minimizing way. So this is also very much related to kind of distance minimizing extensions of curves. A little remark is that this flea condition always implies flea condition, but not the other way around. So do we actually go beyond simplicity here if we only assume flea conditions, let's say, on our manifold? So all simple Riemannian metrics will always be flea epsilon for all epsilon. So that is true. And then we also showed in this article that there are some radially symmetric Riemannian manifolds which have strictly convex boundaries and also interior conjugate points, which are flea epsilon for some epsilon. So we really can allow geometries that are not simple. Conjugate points are allowed. Okay, and this is, I think, where I end my talk, is with the result that we also show in this article, is that now if we have 2 compact length metric spaces, so length metric space examples are, for example, manifolds with closed measurement sets, and they have diameter bounds, and both spaces are in this flea class. Then and there is a homeomorphism between these measurement sets. Then you have Lipschitz stability in the Gromov-Hausdorff distance to Hausdorff distances. Okay, so in particular, this contains, as an example, gas giant metrics. So with basically the same assumptions, you can apply this to gas giant manifolds and say that, okay, this travel time data, Lipschitz stably recovers your manifolds here as well. So we can go a little bit beyond simplicity. Okay, not to go without mentions, the Hölder stability of these kinds of inverse problems was, I think, first studied by Katsura, Kururaba, and Lassos in 2007, and Lipschitz stability for simple manifolds was established by Ilmavirta, Liu, and Sachs in 2022. Right, so that concludes my talk, I think. Thank you very much, and I would be glad to answer your questions.
Thank you very much, Antti, for the very nice talk. Thank you so much. Are there any questions or comments, please?
I have a question.
Please, please.
Yep.
Thanks, Antti, for the talk.
Thank you.
I was wondering in those cases with alpha between 0 and 2. So since the boundary has funny properties, do you still think that the, say, like the inward pointing boundary still makes sense as a model for geodesics, or?
Yeah, so that is a very good question. So basically, you can just use those like level sets of the Hamiltonian, for example, if you want. So you can use inwards pointing boundaries. You see there's like 2 components of the Hamiltonian level set. So one of them should correspond to inwards pointing, and one of them should correspond to outwards pointing. But that's not going to give you like a nice bundle structure, right? Because you're basically it splits into 2 parts. So the kind of fibers of this bundle-like thing are not really like good fibers. So in a sense, yes, but there is kind of an open question whether we should somehow maybe compactify this or do some kind of other construction on top of the boundary to get a better space of geodesics, if you will. So I cannot answer that like precisely, but yes, it does make sense, and yes, the flow does make sense to the boundary or from the boundary, but it's not clear what kind of structures you should impose there to like have nice mapping properties, for example, for the X-ray transform and so on.
Right. Thank you. And slightly related is so could you push the Pestov identity to having a boundary term? Like is there any way to make sense of sort of pinning down the boundary term?
Yeah, I think you could. You just need to worry. Okay, so it's unclear to me what, for example, the measure should be with respect to which you integrate over the boundary. So maybe you could use these age measures to do something there. But yeah, I mean, it's not exactly clear to me how to do that as well, because it's hard to make anything live on top of the boundary. So maybe if you can answer the previous question of what precisely the space of geodesics should be, then you could maybe come up with a nice way of inducing measures from G to this structure, and then you could talk about these boundary terms correctly. But I bet you could do some kind of Pestov type estimate where maybe you replace your volume forms or your measures on the boundary with something that is well defined, but you you will have the correct type of estimate still working there. So maybe not an identity. Establishing an identity, you need to answer this first question
Right.
properly about boundary geometry. Right.
Thank you. Thank you.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? Okay, if not, thank you very much, Antti, for the very nice talk. Thank you so much. Thank you.
Thank you.
Thank you.